Hey, what's up, everybody? So, I guess I keep with the walking music. Here we go. So I always start my presentations with a joke. It's kind of tradition now, so here we go. I'm getting a little bit experimental and abstract with things now, but why did the human cross the road? All right, come on. Someone from the front. Why did the human cross the road? Nothing, everyone's quiet. To get to the other side. Why did the Buddha cross the road? Come on, this is an easy one. Also, to get to the other side. Yeah. Why did the superintelligent artificial general intelligence cross the road? Yeah. Yeah, come on, you know this one. Yes, exactly, to get to the other side, correct. So, I have sort of 3 rules for putting together a talk. That's 1, have something to say. 2, tell a story. 3, be honest and be humble. And 4 is always break the 4th wall. So this is one of the hardest talks. I'll start in reverse order. I'll start with being honest. This is one of the hardest talks I've had to put together. I mean, the technical aspects, I can breeze through that. But I wanted to figure out what the emotional core was. And so I'm sitting in the hotel yesterday at like 5 p.m. and it finally comes to me and it comes together. Luckily, I went for a walk down by the river and the sun was shining on me and I realized kind of how to tie everything together. So what is embodiment? Embodiment is being completely immersed, enmeshed, embedded in the world. It means continuously acting and experiencing, acting again, and then experiencing the consequences of those actions, what happens after. It means learning continuously from feedback without breaks. It means one life. It means not being able to undo, not being able to reset. So, who here in their life has made a decision they've regretted? I my hand's already up. There we go. Yeah, I see. What about had an experience that changed your life forever? We've got a few. Okay, well, go out there. You know what you need to do for the people who didn't put their hands up. So, I'm going to propose to you a thought experiment. Imagine this. You are going to play chess against Magnus Carlsen, the world chess champion, the GOAT, the greatest of all time. You're going to lose. Or maybe Ivan, I don't know. Maybe Ivan's not going to lose, but I'd lose. So now imagine that I let you take back as many moves as you want. You make a mistake, you can go back. You get to the end, you lose, you just go back. You can go back to the start if you want. You can never lose, you'll win, but this would be meaningless. Why? Because for embodied beings, irreversibility matters. Life is a series of irreversible choices. In some sense, the root of meaning is irreversibility. It cannot be undone, but that's what it means to be embodied. Now, I'll give you another sort of interesting thought experiment you can do in your head. Imagine you're cooking on the stove and you burn yourself, and you see the burn on your hand. Now you can imagine it healing. You're going backwards. And this is a fascinating thing because we normally think about models, world models, to be as accurate as possible. You want them to be accurate to reflect the structure of the world, but you can't heal instantly in the real world. Your cognitive ability allows you to reverse the irreversible in your mental simulation. And that interplay between your reversible model and the irreversibility of your decisions, I think, is in many ways the essence of cognition. So this story will be about a company called Cortical Labs, which I was a co-founder of, and I will talk about the importance of embodiment, how it steered our company, and I hopefully have something kind of for you to take away at the end. So the Cortical Labs story. I guess this is going backwards now. Tell a story. So I just want to say this image is not AI generated. It looks like it is, but this is a real false color image from cells grown in our lab. And to kind of set the scene with some characters, here's the other brilliant early people in the company. This is a brilliant neuroscientist, Brett Kagan, and a medical doctor and multi-talented hustler, Hon Ling. And we have this crazy idea, no money, no investors, no lab. And I remember having this situation, we're sitting in the lab and we only had enough money to do a few more experiments. And I remember saying, look, we're stabbing in the dark, but let's hope we're stabbing for an elephant, because then we'll hit something. And if we're trying to stab a snake, we're not going to, and we're going to go out of business anyway. So I don't know, a lot of entrepreneurs won't tell you that story, but I'm trying to be honest and humble in this presentation. So this is the substrate we're using for our dish brain system. So what is dish brain? It is a brain chip. So that means we have a bed of microscopic electrodes and we grow cells, live neurons inside. And they live in a simulated world. And not only do they live in that world, they learn to act. They are embodied in that world. They can sense and they can act. So if you look in the center here, that tiny area has thousands of electrodes. And you could think of in a classic brain-computer interface, you have the brain and the interface is implanted inside. We're doing it backwards. So we have the interface and the cells grow inside. It's a brain without a body, but can sense and act in a simulation. So here is a scanning electron microscope image of the level of integration between the tissue and this electrode substrate. And you can really see, so those little squares in the background, each one of those is an electrode, which is sensitive to changes of like 10 millionths of a volt. They're incredibly sensitive. So if there's any action potential along any of these protrusions, we can detect them with the right digital signal processing. Here's a zoomed in version, and you can really see how close the tissue is growing to these electrodes. It gives us incredible fidelity. It gives us a huge amount of bandwidth and a huge amount of control. So here's a schematic diagram of how our system works. You can see that basically there is the tissue culture, and we have certain regions. This is in our prototype. There were certain regions which correspond to acting. So just like you have a motor cortex, this is a simulated motor cortex. Activity there is moving this paddle in the game Pong. There is also a sensory region, and we're stimulating there. So every time you take an action, or it takes an action, there is a sensory stimulus indicating, giving information about what it's sensing. So this is a fully closed loop, and I think the fidelity and latency we achieved was absolutely unprecedented in the world. It was milliseconds between detecting spikes on thousands of channels simultaneously and delivering feedback about what's happening, delivering a sensory stimulus. So how do we actually shape behavior? So it's one thing to just take neurons and sort of plug them into this simulated world. But what we really wanted to do, and I think one of our really interesting sort of keystone achievements, was showing that we could create directed behavior. What does that mean? It means that it played the game better as it spent more time inside the simulated world. It learned to play the game. And we used this thing called the free energy principle, and I'm going to try and summarize a lot of research and big ideas in a very small, compact package. But the key idea is that the brain is a prediction machine, or a cognitive system is a prediction machine. But when you think about it, if you want your incoming sensory stream to be predictable, there are two things you can do. One is to have a better model of the world, so your inputs are more expected. But another one is to act in such a way that your input is more predictable. This is called active inference. You are acting to make the world more predictable. And you could think of it as something like if you build a house, when it's inside, the weather inside the house is very predictable. That's something we like. So overall, this idea taken into the abstract says, well, in a neural system which is trying to reach an equilibrium, introducing unpredictable stimulus, introducing noise, will create a desire to avoid that noise. So by using random stimulation as a kind of nails on the chalkboard, as a negative feedback, we're able to, in vitro, shape the behavior of these cell cultures. But we haven't been resting on our laurels. So that was a prototype project, and we showed that it could be done. The next thing we needed to do, obviously, is scale up, expand, allow other people to do it in their labs, in their data centers. So we've been working on the production system. This is the CL1, and this is like the very Apple-style slide. So huge improvements from our prototype system. It can respond 5 times faster than before, so we've got response times down to about 1 millisecond. So that means the time from when something happens in a neuron to where we can process the stimulation and send back stimulation is now around 1 millisecond. There's a lot more stimulation electrodes, so we can greatly expand the sort of scope and bandwidth of incoming sensory input. And this system is a closed-loop perfusion system. It's a life support system, which means that you can keep cells alive inside it for extended periods, and they can be continuously embodied. So this 6 months, we have almost very shy of 6 months cell lifetime tested. So that's world-class, and it means that you can run, if you choose, very long embodiment experiments. I have a blank slide. Amazing. Is this a video or an image? It's an image. Okay. Well, when you have this embodied system, this thing that is actually doing cognition, what you really notice is it gives you a huge amount of power. So we're moving towards enabling drug discovery. And how do we do that? Well, we took a known anti-epileptic drug, an anti-seizure drug, and then we collaborated with a team that provided us cells that were a model of epilepsy. So that means this is a cell culture which has certain properties that would be associated with the disease epilepsy. And we plugged them into our simulation, and they didn't learn, they didn't play the game, they couldn't think. Then, as we introduced this anti-epileptic drug, this anti-seizure drug, performance increased, performance improved. So we saw an ability to actually understand and test the effect of a sort of brain treatment or test one of these drugs inside an actual simulation to know what its cognitive effect is. And this is like really, 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 I think, game-changing for many areas of drug discovery, because when you think about it, a lot of the early ways we did this would just be to measure some basic statistics about whether neurons were firing more or less. This allows you to actually measure and understand the effect on cognition. And we even had certain nuances which could be measured in neurons that were interacting with an environment, so actively embodied, which were not measurable in neurons at rest, simply spontaneously firing. And so the company itself and also associated research is really showing that embodiment is a really key part of sort of the neural process, and being able to reproduce that in the lab is incredibly important. So to summarize, we started off and we had a team, and we had an idea. As we built up and we built up and we built up, we showed that you could teach a piece of brain to do something outside of a body. We've been working on continuous embodiment for cells, meaning that you will be able to do this in a lab around the world, collect the results. We're incredibly proud of it, and we already have a few teams who are working on pilot research projects, and we have a lot of interest in the pipeline. So that's incredibly exciting. So I wanted to come back to the sort of emotional core of this talk, which was really important to me. And I think returning to irreversibility as meaning, we think a lot about statistical models, but I think asking if an LLM understands language is like asking if a weather report or a weather forecast understands rain. It can't get wet. It can't experience getting stuck in the rain. It can't experience the feeling of wistfulness as the drizzle falls. I, in my life, have sometimes put off trying to make big decisions because I wanted to have some kind of out, because I wanted to have some kind of way to take it back. And I think when you're sort of running on this treadmill, sometimes all you can think is just keep running. But when you get off the treadmill and you look at yourself, you think, where was I running? Why was I running? Where was I running to? So put up your hand if you've ever put off a choice because of its consequences. Yeah. See, I'm really the same. So if you get one key takeaway from this talk, it's not so technical. It's a little bit about technology, it's a little bit about philosophy, it's a little personal. If there's been some experience that you're craving, some big decision that you're trying to make, try and remember and take solace in the fact that life is a series of irreversible decisions. The reason why you aren't an algorithm is because you are embodied. And the essence of that embodiment is choice after choice and experiencing and choosing and experiencing. So what could be more important to embodied being than that? So I will say, recharge your batteries, go choose, go experience. Thank you.